Our Earth is a dynamic world. Layers of rock and tectonic plates are constantly moving, colliding with each other, moving apart, or slowly shifting. Beneath the crust lies a mantle with extremely high temperatures and pressures, sometimes pushing magma upward through a system of magma pipes and weak fissures. The interaction between volcanic systems, magma activity, and tectonic strain can produce earthquakes, surface deformation, hydrothermal eruptions, and even massive explosions if the pressure reaches a critical point. In the Yellowstone area, we are in a supervolcanic zone, meaning a large magma reservoir sits deep within, heating groundwater and producing thousands of hydrothermal features, geysers, hot springs, fumaroles, and mud pools. Magma activity and underground gas pressure can trigger geophysical phenomena, small tremors, earthquakes, ground deformation, pushing or collapsing, geyser eruptions, and, in extreme cases, volcanic eruptions. In the 48 hours leading up to October 2, 2025, the Yellowstone region and its surroundings experienced extraordinary geological events, 4 major incidents that shook the scientific community, visitors, and residents alike. In the early hours of those 48 hours, an exceptionally powerful tectonic earthquake, measuring 7.3 on the Richter scale, occurred near Mount St. Helens, Washington. This tremor was followed by repeated tremors extending hundreds of kilometers. Initial reports indicated severe damage to homes and infrastructure near the volcano's base, cracked roads, and rock slides on steep slopes. Volcanically, large earthquakes near volcanoes often indicate significant movement within the crust, perhaps rapidly moving magma, accumulating gas, or changes in the pressure of the rock pushing upward. At St. Helens, scientists have long noted a slow magma recharge that appears to have been underway before this event. However, an earthquake of this magnitude has never been recorded in modern St. Helens. It transcends the paradigm of ordinary activity. From a volcanologist's perspective, these tremors could damage underground systems, rupture gas blockages, or force magma to move to new locations. Not far from St. Helens, Mount Rainier, long considered one of the most dangerous volcanoes in the Cascades due to its lahar potential, was suddenly shaken by hundreds to thousands of small earthquakes, with a peak quake measuring 3.9 magnitude. This tremor surged above normal background earthquake activity, and many of the second quakes occurred in clusters, swarms. Seismologists noted that this pattern differed from purely tectonic-style earthquakes. Many quakes were shallow, a few kilometers below the summit, and occurred in a spatial pattern surrounding the magma conduit system and the circulation of hot fluids. In Rainier's historical record, such earthquakes have occurred on a much smaller scale. The increase in earthquake activity at Rainier suggests that gas or magma pressure may be redistributing. This could indicate new magma accumulation, gas release, or changes in the igneous system beneath the summit. Scientists are on edge. Is this just another hydrothermal shock, or is it a step toward a more active volcanic phase? Moments after the devastating earthquake activity that rocked the region of 2 giant volcanoes, the world witnessed an extraordinary natural phenomenon. The massive eruption of Steamboat Geyser in Yellowstone National Park, coinciding with the 34th eruption of Mount Kilauea in Hawaii. Steamboat Geyser, known as the world's tallest geyser, spewed hot water and steam under incredible pressure after a long period of dormancy. The eruption produced a column of hot water nearly 45 meters high, creating a spectacular spectacle that testifies to the powerful energy stored beneath Yellowstone's surface. Researchers suspect that this massive eruption did not just happen. Seismic activity, specifically a previous major earthquake, is believed to have played a significant role. This shaking of the Earth's crust likely caused pressure changes and shifts in the magma system beneath Yellowstone, ultimately triggering the tremendous pressure released through Steamboat. This geyser is fascinating to scientists because of its high sensitivity to changing geothermal conditions. Each eruption is a window into Yellowstone's subterranean world, a world of hot fluids, pressurized gases, and volcanic energy that could explode at any moment in a thrilling display of nature. This eruption is breathtakingly beautiful and a powerful reminder that an unfathomable, ancient force lies beneath Yellowstone's beauty. The 34th eruption, which occurred shortly after Steamboat Geyser's activity, has sparked intriguing speculation among scientists. Although Steamboat Geyser is located deep in Yellowstone National Park in the United States, some experts believe that increased global hydrothermal activity could reflect an as-yet ununderstood global stress pattern in the Earth's crust. However, the primary focus remains on Halema-Umu. The lava erupting with incredible force on the southern flank, nearly half a kilometer high, is no ordinary occurrence. This height is one of the highest recorded in recent decades in Kilauea's shallow eruption history. Meanwhile, the lava flow on the northern flank appears more calm, but no less significant. Its northeastward movement has slowly begun to create a new layer of lava over the old volcanic soil, forming a fresh relief that has quickly transformed the landscape. Experts note that the lava texture in this episode is denser and contains high levels of pyroxene crystals, indicating that the erupting magma originated at greater depths and carried a new composition. One of the most surprising changes in this episode was a drastic reduction in volcanic gas emissions, particularly sulfur dioxide. In previous eruptions, this gas could reach thousands of tons per day. Now the figure has plummeted to just hundreds of tons. Visually, this has made the sky above the crater appear clearer, and less of the yellowish-white haze that typically shrouds the area around eruptions.